And rely.
Scared the heck out of me. I forgot about that. Good gosh. Good old Ann. Ann Serkey. You'll explain the joke to her. Okay. Mark your own quiz. Here we go. How much work is done? Well, work equals force times distance. And this one I've kept fairly simple, a little one marker. So we have a force of 767 newtons, 28 meters. It's two students, but I think both of them push together with a force of 760 newtons as opposed to doubling it. If you did double it, I probably won't take marks off because it's not particularly clear. But 767 times 28, 21,500 joules of work. 1 mark. If they complete this task in 58 seconds, well, power is work over time. It would be, I'll use the actual value, 21,476 divided by 58. 370. Power. Power is measured in watt? 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 Yeah. Never get tired of that joke. It's been 10 years. What work is done by a forklift raising? By the way, what if instead of this question saying raising, what if it had said driving forwards a 688 kilogram box, 2.8 meters? Technically, under our physics definition, no work. No work. Because the force it's resisting is vertical and the distance it's traveling is horizontal. And this is again where I've gone on my rant, Kai, of saying, please don't think that work is fatigue. In English it is, but not in physics. Work equals force times distance. Raising means lifting. You know what? It's really the increase in potential energy. That was our equation that we looked at last day. It's going to be 688 times 9.8 times 2.8. 688, times 9.8 times 2.8. 18,000, I'll say 900 joules of work. How much power does this forklift generate? Power, work over time, which is going to be 18,878.72 divided by 73 seconds. 259 watts. Okay. That means if this was an electric forklift with an electric motor, if the motor could only produce 250 watts of power, you couldn't get the job done in 73 seconds. Is work a vector or a scalar? It's one of the reasons it's so nice. It has its limitations. There's certain stuff you just can't solve with it. In particular, it doesn't work well for collisions, for car collisions, but it works really well when there's a change in height and a change in speed and a curvy path. Work is measured in what units? Well, it's Newton meters. I'll take that, I guess, but we said we're going to call that a joule. Power is measured in watt units. Yes. Oh, no, wait a minute. It's a joule per second, but if you just wrote a watt, I'm good with that. Okay. Turn the page. What is the minimum power generated by a 64 kilogram person who climbs 82 stairs, each of which has a height of 21 centimeters? Nice try. 0.21 meters. You're not going to fool me there. In 83 seconds. 82 stairs in 83 seconds. That's about a stair each second. Okay. Doable. A little tiring. 82 stairs. What is it, about 10 stairs per story? That's probably about 8 stories. Oh, we'll find out. Power is work over time, which I guess is force times distance over time. By the way, little physics 12, put your pencils down. What do I measure distance in? meters. What do I measure time in? What is meters per second? You're going to find another way to calculate power. It turns out it's also force times speed. It kind of pops out of that. Pick your pens up again. Force, mg, distance, height, divided by time. Mass, 64, 9.8. The distance looks like it's 82 stairs times 0.21 meters per stair, divided by 83. How many watts of power? Is that right? You got 130 watts? People nodding? Is that right? Yep. Okay. So they could also, by doing this, they could also have powered a nice bright light bulb with some, or two 60-watt bulbs with a little bit extra. An electric motor lifts the 25-kilogram load a vertical distance in 32 seconds. Okay. I've seen this a few times before. It's work over time, which is actually going to be mgh, force times distance over time. 25 times 9.8 times 24 divided by 32. This might work out evenly. Not quite. 183.75. I'm going to write down 183.75, and then I'll give my final answer to, I guess, 3 sig figs watts. How efficient is the motor? So efficiency had this funky symbol, but you can just write EFF or efficiency or whatever. And it's, you know what? Power out divided by power in times 100%. You know what? It's the smaller number divided by the bigger number. 244 is the bigger number. 183.75 is the smaller number. Divided by 244, 75% efficient. Mr. Dueck, what if we left it as a decimal? If you wrote 0.753, I'm okay with that. If you wrote 0.753 and put a percent next to that, no, half mark off, because 0.753% would be 0.000753, right? Remember your Math 8 from back in the day? Last one. A 65 Newton force is horizontally applied to a mass of 12 kilograms sitting on a level floor for a distance of 14 meters. How much work did... So, the work done by the applied is going to be the applied force times distance. And they gave me the applied force. 65, distance, 14. Don't need to multiply by 9.8. This isn't vertical. The applied force was 65. It's already in newtons. Apparently, we did 910 joules of work. How much work does friction do? Gravity down, normal force up, applied, friction. Okay, work done by friction is going to be friction times distance, where friction is mu times the normal force times distance. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. It's going to be mg. Mu mg d. It's going to be 0.25. Mass 12 g. 9.8. Distance 14. The work done by friction $411.6. Is that right? Technically, no. Now, I'll give you full marks if you said the work done by friction is 411.6. Why is that technically wrong? Uh-oh. Yeah. Well, I'm just going to say I would call that negative. I would say technically you're losing energy to friction. Now, if you didn't put the negative here, I won't freak out as long as you subtracted here. Okay? In other words, what's the net work done? The net work is going to be the work done by the applied, take away the work done by friction, but don't go minus minus becomes a plus. It's going to be 910, take away 411.6. $498.4 joules of work. Any lawyering, any questions, anything you're wondering about? Can you give yourself a score at the top of the quiz out of, count 'em, 13? Make sure your name is on it and pass them inwards, please. So continuing from where we left off, we said this. And for those of you who are away, don't try writing all rundown. The law of conservation of energy said that the amount of energy before had to equal the amount of energy after. Now, there's all different types of energy, Chi, but we said here in Physics 11, we're going to look at two main types. Kinetic, the energy of motion, which was a half mv squared, new equation, and gravitational potential, which we just called potential, which was how much energy you had due to your height. It was mgh. And so the law of conservation of energy, McKinley, was this. The amount of kinetic at the beginning, initial, plus the amount of potential at the beginning, initial, has to equal the amount of kinetic at the end and the amount of potential at the end. Or if the question mentions that we have lost something due to friction, we said it's the same equation, plus there must have been some heat left over. So we looked at the skateboard park, the virtual skateboard. We looked at my wonderful energy transfer device that's on the board behind me. We looked at a few examples, and I said, conservation of energy is really handy to use. It's really great for analyzing when you have a change in height, a change in speed, and especially a curvy, yucky path, like skiing or roller coasters. So we said this, a roller coaster is traveling as shown below. At point A, it's traveling at 12 meters per second. How fast will it be going at the bottom? We said, is there a change in height? Say yes. Yeah. Is there a change in speed? Yeah, it's going to speed up. Is there a yucky, curvy path? This is why a scalar approach, where vectors are not necessary, is so nice. B, so we found that if there was no friction, the roller coaster would be traveling at 22.3 meters per second. By the way, I love example 5. I love example 5. I love example 5. Yes, but also I love it too. Not just that it's going to be on the... It's a roller coaster! Okay, sorry. So B said this, hey, what if turns out the roller coaster, maybe we got a radar gun at the bottom, which I have, and it's only traveling 15 meters per second at the bottom. How much energy was lost to heat? Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. Are they talking about heat? So I'm going to modify my equation. It's going to be kinetic initial plus potential initial equals kinetic final plus potential final plus heat. How many more am I doing? Tarzan. We finished with Tarzan. Yeah, good. Okay. What are they asking me to find here? I'm going to get the heat by itself eventually, but first I'm going to say, are any of these 0? Is my initial kinetic 0? And really what I'm saying is, am I at rest at the top? No, look at the picture. It says I'm going at 12, yes? Is my initial potential 0? Really I'm saying, am I starting out on the ground? No. Is my final kinetic 0? Am I coming to stop at the bottom? No. What about my final potential? I'm ending up on the ground. How would I get the heat by itself? And I don't know why, But this, if you ask me what single mistake drives me craziest the most in Physics 12, it's because I'm sneaking some Physics 12 in with you, by the way, here. It's this right here. This equation right here. This example right here. Because for some reason, I see kids want to divide by kinetic energy. I don't know why. Is the kinetic energy multiplying onto the heat? No, it's adding. So how will I get it by itself? Subtract. Yeah, I'm going to get this. Kinetic initial, potential initial, minus kinetic final. Whatever's missing, that's what you lost to heat. Heat equals, what was the equation for kinetic energy? This was our new equation. Don't have to memorize it. It's on your sheet, but it's worth memorizing because you're going to use it so often. A half m, and I guess initial would be v initial squared plus, what was the equation for potential, gravitational, for potential energy? So I guess initial is going to be mgh initial minus, and I guess a half mv final squared. Now, we did notice read last class that in part A, the mass canceled. I said there was a reason why when you went on a roller coaster, they didn't make you step on a scale. They didn't have to carefully balance everything. They didn't have to make sure that two huge fat people didn't sit next to each other or two really skinny people didn't sit next, because the mass cancels. Ah, but here, does the mass cancel? I heard someone say yes. I heard someone say no. One of them's right. Is there a mass? Is there a mass in this term here? Yep. Is there a mass in this term here? Is there a mass in this term here? Kai, is there a mass in this term here? So does the mass cancel? No. Turns out friction does depend on how much mass there is. Fair enough. In real life, though, roller coasters are really well greased. So how much friction is there? Not none, but close enough to none that for all intents and purposes in real life, the mass does cancel, which is why you don't have to step on a scale before you go on the rides. I don't know if you ever wondered why you don't have to, but that's why. So heat is going to be 0.5. Did I give you the mass of the coaster? Yeah, 245. 245. What's the initial speed at the top of the hill? I've scrolled down. Was it 12? Yeah. Squared? Yeah. Plus 245. 9.8. Was the height 18? I'm going from memory here. Yeah. Minus 0.5. 245. And looks like we clocked it at 15 meters per second. And don't forget the squared. That last squared is the one kids forget the most often because they're so proud they've done all the physics and they let their guard and they forget the squared, especially typing it. So get your calculators out. You should be able to type that in one fell swoop. And tell me how much heat. Whoa. What the heck happened here? Uh-oh. And we're back now. Okay. I was typing away and not looking. 0.5 times 245. I was typing and nothing was showing up. 245. By the way, I'm expecting a positive answer because heat was generated. Do you get 33,300 joules of heat? law of conservation of energy. Energy's got to come from somewhere. The amount of energy before has to equal the amount of energy after, and if it doesn't, you've lost some to, in real life for a roller coaster, by the way, Valoria, heat and sound, because I've heard that they make noise. Okay. You know what? Probably also to air resistance, because a roller coaster bumps into air molecules, and each of those air molecules absorbs a tiny bit of kinetic energy, although they do design roller coasters to look pretty aerodynamic for that reason, right? Example 6. It's 2 more, right? Yeah. A 25 kilogram object is dropped from a height of 42 meters and it lands in the snow with a speed of 25 meters per second. How much heat energy was produced during the fall? Shaq, what's this question asking me to find? How much heat energy? Is there a change in height? Is there a change in speed? What's V initial? What's V final? So, ready? Scene 1, Act 1, Take 2. Is there a change in height? Change in speed? Yeah. There isn't a yucky, curvy path, but the fact that they also said how much heat energy, you know what? I think this is a job for conservation of energy. But they're also talking about heat, so I'll do the one that has the heat attached, right? Kinetic initial, potential initial, kinetic final, potential final, and heat. Are any of these 0? Oh, dropped means I'm starting at rest? Oh, I'm hitting the ground. Cool. So I'm going to get this. Oh, before I go to the next line, also, how would I get the heat by itself? Okay, so I'm going to get heat equals PE initial minus KE final. Yeah? So heat is going to be mgh initial minus a half mv final squared. And this is nice because up until now, anytime I've looked at projectiles or dropping, we did free fall earlier, and we solved it with a different method. There we really couldn't look at air resistance or anything like that. Now we're saying, oh, we can start to analyze air resistance a little bit. Mass, 25. G, 9.8. H initial, 42. Minus 0.5. Mass, 25. Speed, also 25. Squared. How many joules of heat were generated while it was falling? Now, this answer won't be that big, but I'm telling you, when meteors from outer space, which are going way, way, way faster, hit the atmosphere, they generate an awful lot of heat. Okay? Or, heck, when our space probes, like the Soyuz space rocket, or when the space shuttle comes in, it generates an awful lot of heat. We okay there? Yeah, I noticed. That was free fall. That was a few units ago. 25, oh, turn the calculator on, Mr. Dueck. 25 times 9.8, wait, times 42 minus a half times 25 times 25 squared. Do you get 2,480? All right, 2477.5. 2477.5. By the way, technically, how many sig figs should I go to in this answer? I guess technically 2, so 2,500 joules of heat. And I said I'll try and be correct on sig figs, although I've been sloppy the last couple of days. Example 7. Tarzan, woohoo! Weighs 82 kilograms, and he can run at 8 meters per second. He runs along the ground and grabs a vine, swinging into the air. What we're talking about is this. He's going to run along the ground, grab the vine, and when he hits it, swing into the air. Anthony, is there a change in height? Yeah. Is there a change in speed? Is there a yucky, curvy path? How might you analyze this? Conservation of energy, you say. Oh, you are ever so clever, Anthony. We get this. Anthony, plus heat or not? Read the question. Is it wanting me to include friction? Does it? Okay. Good. Mr. Dueck, yes, Anthony, oh clever one. I got a problem with this. Why? Well, Mr. Dueck, Tarzan's feet are on the ground, but he's grabbing the vine up here. Shouldn't we have to take that into account? One of the nice things about energy and about conservation of energy is you can put 0 wherever you want to as a height. How about let's put 0 right at the bottom of the vine? We're allowed to. Makes our math much nicer. Okay? So even though I agree with you, technically the vine isn't touching the ground, mathematically it can be. Are any of these 0? Now again, here's what we're talking about. So let's look at the bottom here. Is my, and I'm not talking about right now, I'm talking about right now. Is my initial speed 0? No. Is my initial height 0? Ah, cool. So I can go, ha-ha. What about my final kinetic energy at the top? How fast am I traveling at the top of the swing for a split second? 0? Really? How high am I at the top? Oh, the definition of the word top means not 0 high, so don't cross that out. In fact, I get... Oh! Before I do that, so here's what that means. The fact that this mass cancel says not only could Tarzan swing up to whatever height we find, Tantor, the elephant, if he could run at 8 meters per second, and if the vine could hold him, he would swing up to the same height as Tarzan. Or, how many of you have ever been on a rope swing? I don't know if you ever noticed, but how high the person gets at the peak does not depend on whether it's a small person or a big person. It's all about how high they start and how much of a run they get at it. But otherwise, they hit the same height. Or you can even notice it with this. See, I'll eyeball it. With one mass, I'll go about that high. With 2 masses, I'll go about that high. I think they both got to about the same. I could really muck around with this, but minimal friction with a rope swing. There is some, so technically it wouldn't quite get to the same height, but really close. No friction. Now, what are we trying to find? It was Darian. Final height. How would I get the h by itself? Don't have to divide by mg. What do I just divide by? Oh, very cool. So the final height that he gets to is going to be v initial squared. You know what? I'll put the 2 down there instead of having a 1/2 in the front. That looks a little cleaner. In fact, I can almost do this in my head now. Final height is going to be 8 squared divided by 2 times 9.8. 8 squared is 64. Divided by 2 is 32. 9.8 is really close to 10. It's going to be really close to 32 divided by 10. Your answer is going to be like 3.3 or something like that. 3.265. You know what? 3.3 meters. 3.3 meters. Where does conservation of energy shine? Lots of locations, but for starters, roller coasters, ski hills, and rope swings. What's your homework? And I got some cool videos to show you. Number 1. Two is good. Lots of steps there. Partially bagged, filled with cement. Meh. I'll do skip 3. 4 is good. Five is fine. 6 is good. We'll skip 7. Part 2, a little more conservation of energy. 2 is good. Three is good, skiing. Number 4, very important. So can you all look at number 4? Number 4 says this: a golfer wishes to hit his drives further by increasing kinetic energy of the golf club when it strikes the ball. What would have a greater effect on the energy transferred to the ball by the driver? Doubling the mass of the club head or doubling the speed of the club head? Speed? Why? Did I do this rant with you already? No? Kai, why? Okay. If I double the mass, I only have twice the energy to give to the ball. But if I double the velocity, how many times more energy do I have to give to the ball? 4 times. And this has had a huge impact in the past 20 years in sports. So back in the 70s and 80s, golf drivers, for example, were getting heavier and heavier heads. It was almost like a sledgehammer. Not that bad, but close. And then people clued in, actually, we need to make equipment lighter. Rackets have gotten lighter. Hockey sticks have gotten lighter. Tennis rackets have gotten lighter. Golf clubs have gotten lighter. Why? It's a trade-off, Dane. You lose a little bit in the mass, but you more than make up for whatever it is in the club head speed, and that's way more bang for your buck. Because if you can triple your club head speed, that's 9 times more energy to play with. Even if you're half the mass and tripling the energy, you're still going to have 4.5 times more energy to play with. So that's all sports equipment has gotten lighter over the years. We just did number 4. I guess you can omit it, but we just, okay. I'll let you try number 5. It's tricky. Actually, no, cross out number 5. Underneath number 6, write that. Work is, I'm going to actually do this next lesson, but a preview. Another way, work is force times distance, but another way to do work, it's the change in kinetic energy. What's change in anything? Final, so if you go kinetic energy final minus kinetic energy initial, that will tell you how much energy it takes to speed up. Seven, I'm going to pass on. 8, I'm going to pass on. So we'll stop there. Okay.